Hi, thank you for being here today. Fast Data Theater, in case you're not in the right place. So I'm going to be speaking today about fast data. I'm going to be speaking about an open source database. It's called QuestDB. And I'm going to tell you why we are building this open source database and how we are designing it internally in order to make it perform fast. Here for the clickbait, I have ingesting 1 million time series per second, and we can do that. We can do better. But it's not really important that we can ingest over 1 million time series. It's more about how we think about performance, how we are designing all the database in order to make it work like that. My name is Javier. If you need anything, any question, anything you want to know about QuestDB, you can ask me. But we also have a stand here, a booth. It's right over there. We have the CTO and the CEO of QuestDB are there today. And the CTO is the one that knows better than anyone about performance. So if you have anything, happy to answer. But also, just go by the booth, and it should be cool. So I don't know you, but when I go around this nice expo, I see a lot of data vendors that tell me, hey, we are the solution for all your data problems. And I don't know, man. I've seen different kinds of data problems, and they all look different to me. Yeah, sure. I mean, if I have a single tool to do everything, that's great. But only when you have one thing to do everything, you cannot really optimize for any particular use case. And when you really need the performance, you need to optimize. That's kind of the deal here. So we are not trying, or QuestDB, we are not focusing on every kind of data problem. We are focusing on a very specific type of data problem, which is time series. So anyone here working with time series data? Hey, thank you. Thank you for that. Cool, cool. With any time series database, or just in general with one of these I do everything database? So general? That's good, because generic databases can do everything, and they can do it quite well, up to a point, okay? So maybe some of you have a time series problem, but you still don't know it. So that's the first thing. And we started building QuestDB because of that. We had, our CTO was working for a bank at the time. I know, boring, but banks, you have to love them. So he was working for a bank. He needed to work with big data, with a lot of data, fast-moving data. He couldn't find an open source solution that could be easy to use for dealing with time series. But how do you know if you have a time series problem? Well, there are some indicators. For example, most of your queries might be limited to a time range. Imagine, I don't know, how much is overheating my nuclear reactor in the last 30 seconds. That's a real use case for one of our users. Or it might be the case that you're mostly inserting data. You are not really updating or deleting data. I don't know, imagine you are market exchange and you are working with trades. You are getting new data all the time. You don't update the value of, what was the value of a trade 1 minute ago. You just don't do that. So that's another indicator. It might be that you often write more data than you read. Yeah, with IoT, with market data, we see that a lot. Maybe you are ingesting data. Oh, that's a good one, another use case for one of our customers. Maybe you want to optimize the engine for a spaceship, and you are getting a lot of metrics, but you are only analyzing once in a while. So you are getting much more data than you are reading. And in the end, it's going to grow that much that your general database can help you up to a point. After that, it's like, you know what? I cannot keep up with that. It's like too much data. So those are some of the indicators that you might want to work with a time series database. And then it's also about the semantics. Often you have data with very low resolution. Maybe, maybe you have data coming every half a second. But you want to only have the average per hour. Or you want to join two different data sets that are coming at different speeds, and you want to make sense of those. And you need to resample or to align timestamps. Those kind of things are good indicators that you might have a time series problem, even if you still don't know it. Okay. So yeah, also in time series, it's important. Your recent data is more important than your old data. I want to know what's happening right now with a particular sensor. I don't really care much what happened 2 years ago. I might use it for historical queries. That's fun. but not straight away. So those kind of things, So if you have those things, you might be having a time series problem, and you might be, maybe you might be happy with a time series database. Sorry, it was boring. I'll try better next time. Some people are leaving, Anyway, so to learn this a little bit and to show you what this is about, I'm going to show you some real time series data over open source, over open data sets, so you can see what I'm talking about. Okay, can you hear me here? Oh, yeah. So let me just go. If you install QuestDB open source, you have this web interface to run your queries. Of course, you can just run your queries connecting using a Postgres compatible library, but you have also this web interface, and we have a live demo in which we have some open data sets you can play with. So just to get an idea what you can do with time series, I have, for example, here one data set, which is we are getting trading data from Coinbase. And in this particular query, what we are doing, we have right now in this data set, it's quite small. It's like about 250 million rows, something like that. So we are going to take these 250 million rows, and we are going to be running one particular query in which we get all the data which is more recent than 1 month. We are going to sample the data into 1 day. We are getting data every second. So here we're going to be just aggregating per day. We are going to be getting what was the closing price for every day. And we are joining with the same data set just 1 day before. So basically here, what we are doing is like we are just comparing the closing of the market 1 day with the closing of the day before. Just, simple use case to get started. But let me just for a second, if I can, okay, show you something slightly more interesting. This open data set is tracking positions of ships in the ocean. So I'm going to show you one query, which can be maybe interesting, which is, okay, I want to show you, we want to see which was the latest position for each ID. Every ID represents a different ship. So which was the latest position in this particular geographical area, in this particular time range. So that's basically telling me, oops, sorry, have to select, that's better. So this is just going through a data set, and for each particular ship, for each ID, I'm getting the last time I saw that vehicle, that ship, within a particular area. Again, those kind of queries are queries that you can benefit from when doing time series. But let me just go to something slightly more interesting. Here I have the, you're probably familiar with the taxi rides data set, New York City taxi rides. It's a big one. This one has, let me just show you first, select, count. So this data set is kind of big. It has 1.6 billion rows, which is not bad. 1.6 billion, it's already getting interesting. So what I'm going to do, I'm going to ask from this data set, tell me for all the trips that happen from June 1st, 2018, and 1 week after, so we have some semantics for making working with data range easy. So for this week, and sampled by 1 hour, tell me how many trips we had in this particular data set. And sure enough, in about not even 200 milliseconds, we are just filtering the data, aggregating the data, and telling you for this particular point in time, for each hour, how many trips we're aggregating. It sounds like a straightforward. And the last one I'm doing before I go to the real demo, I'm going to show you one which for me is quite interesting. I have this data set with the trips for the New York taxis. I have a data set with weather information. Weather information is coming only to this data set every few minutes. But the taxi rides, we are finishing several taxi rides every second. So they have different resolutions. But it would be cool if I could join them together. Like, I have this weather data with some timestamps, these rides with other timestamps. And if I use a generic database guy, you are moving around, yeah. If I use a generic database, I can use a query to do this. It wouldn't be super simple, but it's doable. On QuestDB, that's actually quite simple. We have these extensions. So basically here, let me just format. So here what I'm doing is, I'm getting all the trips for a particular day. So I'm getting all the trips that happen in the 1st of June, 2018. I'm joining with the weather table, and we are doing what we call an as of join, which means I know these two tables have different timestamps, different resolutions. Do your best and match every row in the left table with the closest timestamp from the right. So if I have only information about weather every 10 minutes, and I have information about taxis every few seconds, for each row for a taxi ride, it's going to find the closest row, in the other data set. And if I run it, yeah, there it is, in 50 milliseconds, I'm joining the taxi ride with the closest, And again, you can do this with a generic database, yeah. But when I'm building specifically for time series, you have these kinds of extensions. Does it make sense? So that's what we are talking about. Going back to the, yeah. So that's what we're talking about. But if you remember, I started telling you, I'm going to be ingesting a million rows per second on a single instance. I could have said 1 million. I could have said 1.5. I don't care. I call bullshit. Because it sounds impressive, but it means nothing. Ingesting 1 million records per second on a machine is super straightforward. Just give me data, I put it on disk, I don't do anything with that, that's it. I'm ingesting data. And you're going to find that often in every benchmark, including ours, which tell you things that don't make sense. It's like, oh yeah, we are super fast. So what? You can ingest 1 million, that's the idea. So the interesting bit is that what are you going to do with that data? That's the interesting part. So in QuestDB, what we are building is an open source database in which you can actually ingest over 1.4 million. That was a year ago. Today we are faster, but I don't care about how much, because in real life, we don't see users ingesting 1 million time series per second. It's possible, but it doesn't make any sense for you. So our users, the heaviest users we see right now in QuestDB, they are sustaining writes at about 100,000 records per second maximum. Those are the top customers every second of the day. That's true. But about 100,000 records per second, no more than that. You probably don't need to ingest 1 million rows per second. Even if the database can do it, it doesn't make sense. But anyway, so with QuestDB, you could ingest over 1 million, and at the same time, you could be scanning that data at the same moment it's committed. The moment it's committed, we don't have to reindex, we don't have to do anything. It's readily available for being queried. So you can ingest data very fast while you are running queries up to 4 billion records per second, also on the same instance. That's kind of the deal. That's kind of the thing that you can do with open source QuestDB. So we focus only on this type of problems. And since we focus only on problems where the time dimension is critical, we are able to optimize in many things that we wouldn't able to be to optimize if we have to support other use cases. That's kind of the idea, the trade-off here. We are super fast only for doing this. If you try to use QuestDB as your relational database, you are going to be so disappointed. So, that's the idea. That's what we are good at. And if this is working, so we have to decide what we are not going to do. We are not your transactional operational database. We are not that. We are not a data lake or a data mesh or a data warehouse or a data mesh or whichever is like the new data buzzwords. We are not that. We don't try to, we are not machine learning powered yet. We don't have any of those things. Well, we are not a generic database. We are real time, but only for time series. So behind the scenes, we do pretty straightforward things. Yeah, of course, we partition the data by time, of course. We are column-oriented, so when we are doing queries, we don't have to read every column. We only read the columns that you have in the query, of course. When you ingest data, you can ingest using SQL, but it's not super efficient. If you want to ingest faster, we support a protocol called ILP. We have official clients written in C, C++, Java, Go, Rust, Python, and Node.js. Did I say Go and Rust? Yeah, probably yes. So those are official clients. You can also use Ruby or PHP or whatever, but we don't have a client for that. You have to use then the socket library and send the data over socket. But for all the other languages, we have clients available. For reading, we are compatible with the Postgres wire protocol. So any library that can connect to Postgres, you can connect to QuestDB and run your queries. For example, you can have Grafana displaying dashboards using the Postgres plugin. It works out of the box. You don't have to do anything. So that's pretty standard, But the interesting bits come slightly afterwards. So the first thing that I think we are peculiar, let me just check how I'm doing on time. I'm doing fine. So the first thing that we are a bit peculiar is when it comes to storing data. A lot of information here is not going to be on the exam, so don't worry. But anyway, first thing is we are partitioning data. We are storing by column. And there is an interesting bit here. We have a single writer for each table. And then we can have multiple readers. They are completely separated on the machine. We try to use efficient usage of the threads. We have different pools for reading and writing. So basically, even if you are overloading the machine on reads, writes are going to be still efficient. So you always get performant writes, even if you are using all the resources you have for the readers. So we are not going to be, because of you have slow queries, you are not going to be slowing down your writes. The other interesting bit, which is not here, is that I cannot see any indexes there. We don't use indexes. In the past, we used them. We realized they were slower than what we were doing. So basically, what we are doing, since we specialize on time series, which means you usually are filtering by a time range. You usually want to read recent data. You usually want to have the data sorted by timestamp. What we are doing when we write the data to disk, to the table files, we write the data in chronological order. So data is always sorted on disk. So we don't have to do anything weird to resort the data or to scan or whatever. If we get out of order data, we have some interesting internal mechanisms, but eventually we will rewrite everything on disk, so it's sequentially sorted, chronologically sorted. And with that, we don't need indexes, no primary or secondary. Actually, for some columns, we still support secondary indexes, and that's going to be deprecated. Because if you create them, you are using more disk space, and it's slower. So it doesn't make any sense at all. So that's kind of the first thing. And the other thing is that we are a bit peculiar. We didn't write, well, I didn't write the database. It was, it was the core team. I just speak about these things because they are fun. But we didn't write this database because, on top of any other database engine. Oh, let's take this whole engine and add time series. Let's take Hadoop ecosystem and let's add something for time series. It's written from scratch. And from scratch, I mean from scratch. Because it's written in Java and C++, but I don't know if you are using Java or you code in Java. But if you know Java, garbage collection can be a pain. So we are not using Java memory management. We do all the memory management by hand. So we have zero garbage collection across the whole application, which means the garbage collector is not impacting performance at any point. We use direct memory mapping. So we have small parts of the application written in C++, and memory is shared across C++, across C++ and Java. So we don't have to do intermediate conversions. So we can be super fast. Java is cool, and it has super performant libraries for input and output, but we are heavily dependent on performance. So we had to write our own libraries for input and output. They are open source, everything is open source. So, so we don't have a garbage collection there. Same thing for strings, same thing for many of the objects in Java. We have no dependencies, and it's written everything from scratch. And we even implemented our own solution for a logger. Rather than going with log4j, we said hey, maybe we can implement our own logger. Does it make sense? I don't know really, but these are the numbers. These two rows below are log4j. These rows above are our own logger. These numbers here represent how many nanoseconds you spent in a single operation. So writing with log4j, depending if you're doing this write or this one, but writing can be almost 900 nanoseconds. With our library, almost 300 nanoseconds. So I know it's nanoseconds. It's like nothing, yeah? But you are logging all the time, and logs are important. And man, 600 nanoseconds. So that's kind of the thing. That's kind of the deal. So that's why we are doing these things. So we can really be more efficient than any other database when you really need the performance. That's kind of the deal. That's how we think about performance. I don't know if you've seen the movie Taken with Liam Neeson. Has this famous quote, it's a meme. It says something like, I don't know who you are, but I will look for you, I will find you, and I will kill you. So that's how the team thinks about performance. Sometimes they don't know exactly where we can improve performance, but they are going to look for that. They are going to find how to perform better, and they are going to quicken up. They are going to make that go faster. And very often, the answer to make things faster is just taking advantage of new developments in hardware and software. It takes out developers and a developer. We are lazy. We like Google, Stack Overflow, copy and paste. If you see my keyboard, the C and the V keyboard, I paste more often than I copy. I don't know. So I'm lazy. That's why I'm a developer. If not, I would be doing something interesting with my life. But I'm here. Here are. So basically, why I was saying this, I don't know. Anyway, yeah, I know. But I'm lazy. Okay. So the thing is, you keep developing in the same way that you've been developing for the past 10, 15, 20, whatever years. And we assume that things are not improving. But operating systems and hard drives and CPUs, they are magic these days. They can do things they couldn't do 5 years ago. And if you find those improvements, if you take advantage of those things, that's super interesting. And that's what we do. Whenever we see a new CPU maker saying, oh, now in Intel, we have this fantastic instruction set that can help you do this, and this is the benchmark. We don't care about the benchmark. We do our own benchmark. We test the thing out. We see if we can get the improvement out of that. It turns out very often, you can do a lot of interesting things. So things we do, of course, we have memory mapping for having direct memory mapping, which is straightforward. We use SIND. SIND is a fancy mode of modern CPUs to parallelize things. Rather than execute one instruction every time, you can execute one instruction over several records of data. So we parallelize as much as possible when we are reading data, and we have seen stellar performance when using parallelization when you compare to just single thread. An interesting bit here, that was actually interesting, a user on Slack was complaining, I'm running this query, it feels slow to me. We look at the query, it's like, oh yeah, I don't know, could be better, but yeah, it was slow. We didn't know why. So it's like, okay, let's see what's happening. It turns out Java, the JVM virtual machine, is doing some optimizations, but some of them are not really great. So eventually, because we don't have social life, we implemented our own just-in-time compiler in C++, so we could optimize some of the filters and beat the performance of the Java virtual machine for those specific filters. That's kind of the idea. And same thing for input and output. And for these two, before I finish, I'm going to show you a couple of examples about this. So this is one query that is similar to the one that I told you. This query, it goes to the taxi rides, 1.6 billion records. It's doing a couple of filters. The filters are not scoped by time. So we cannot apply our fancy timestamp optimizations. There is no time filter here. Fuck. So it's like, OK. So this was slow. So after writing the just-in-time compiler, we found out in the call run, without the data being cached on the system memory, we went down from 30 seconds to 12. On hot data, we were to 3 seconds, which is not bad. But I was actually running this for the query yesterday. And let me just copy this very quickly. Still here, just a second. OK, so I execute this query. It went over 1.6 billion records in about half a second, 557 milliseconds, OK? Which is which, if you ask me, is not too bad. So that's what I'm talking about. So we were super happy when it was already at 3 seconds. We didn't do anything special to improve this particular query. We've been just releasing new versions every 2 weeks or so. We have a new release. Each release is always at least as fast as the one before. We never release anything in which the test goes slower than the other. So we fix, we add new features, we never get slower. So just by letting time go by and applying new releases, we have faster queries. There's no in the regular, in the regular way of doing things. So that was one of the examples that we had. And the last one I want to show you, interesting problem. Imagine you have a CSV file. CSV, yeah, we love CSV, of course. CSV file, which is big. Imagine, I don't know, 70 gigabytes of a uncompressed CSV, 70 gigabytes, kind of big. And it doesn't fit in memory. Imagine you have, I don't know, 16 gigs of RAM, 70 gigs of a CSV file. It's unsorted, and you need to sort the file. So I told you, when we ingest data, we need to write in chronological order. So we need to, if we want to ingest in batch mode this file, this is a real scenario for us, we have to order first. How you do that? How would you sort this? Well, we had our old algorithm, lot of swapping, lot of everything. It will be slow. So in the past, ingesting a CSV heavily unordered on QuestDB, it will take about 28 minutes on a medium machine, AWS machine, 28 minutes. Okay? So the thing was like, oh, ingesting large data, it's important. If it was in order, no problem. But if it was unsorted, that was the issue. You cannot put everything in memory, sort, and then write. So first, they wrote a first version in which we parallelize everything in small chunks, reorder, blah, blah, blah. And that was slightly faster, but not as much. And then someone had been reading about someone called IOUring. IOUring is a file interface for Linux. It's been around for about 3 years, but it's not widely used just yet. I don't know why. Because it's scary. It's like, am I going to change how I'm accessing this drive on Linux? Yeah, why not? So we went with IOUring to try. So basically what you do here is you parallelize random reads on disk as much as possible. And by doing that, we went down from 28 minutes to about 5 minutes, which is not bad. And again, this is one of the things that in order to get the performance, the only way we found is actually taking advantage of newer hardware. There was nothing we could do in software to make this faster. And these are many of the things we are improving all the time. Just being up to speed with new developments, benchmarking, trying out. I told you earlier, QuestDB is open source. Apache 2 license, you can use it for everything you want. If you are a software vendor, if you are a cloud like AWS, you can take our code, offer QuestDB, get money on top of that. We cannot do anything. It's Apache 2, so you can do it. But if you prefer, if you say, you know what, I prefer to have a managed experience. Easier to manage. We also offer now the QuestDB Cloud. It's actually in beta, but you can join the invite. So you can have the same experience of QuestDB, just managed by the core team. But if not, just go with the open source, which is where all the users are today. We've been around for 3 years. So it's quite stable, it's working fine. So the recap today, working with time series can be hard, but some databases, like QuestDB, there are also others. You will find some other time databases in the expo today, just not as fast, but anyway, So there are other databases, but QuestDB can help with that there. You can engage with ILP and query with SQL. We measure, implement again and again and again to get the most of the performance. And I know the benchmarks are lies, but if you like them, we have all of them available and a lot of interesting writes about the engineering team on our blog post. I invite you to check it. So we are open source. If you start us on GitHub, you will be a better person. You'll feel happier. You'll wake up tomorrow without a hangover you drink today. And yes, if you have more, you want to know anything else, we are right there before the cafe at the QuestDB stand. Thank you very much and have a great day.